Okay, in this video we look at transistors. We're going to look at concentrate on an NPN transistor. A transistor is a current control device. So the current flowing down here is a combination of the current here in the base and the collector. But there's another more important formula I'm going to show you in a minute that shows that it is a current control device. So just as a partial extract of a circuit here, what we find that when the voltage here V in with respect to 0 volts, so when there's no voltage here, the transistor will be switched off. Transistors will be switched off. So the voltage collector to emitter, so the voltage across the transistor, will be switched off. So it's going to be up here. And then as soon as we increase the voltage to approximately 0.7 volt. The reason why approximately 0.7 volt, because we always assume for a transistor to switch on there to be about 0.7 of a volt just here. So we approximate then just to say as soon as V in gets to approximately 0.7 of a volt, then the transistor goes from being off to then off to then on, and it follows a linear path. And at this point here we say it's just saturated, so it's just fully turned on. And so what we can then say that if we use HFE, the current gain of the amplifier, so what we get is whatever current we have here on the base, if we multiply it by the internal gain of the device, will then give us the current that's flowing down through it. Okay, so that's a manufactured stated number or region of numbers, but it's a manufacturer stated for each transistor. So the current gain of the amplifier multiplied by the current of the base gives us the current flowing through it. So that's why it's a current control device. So it's the current that we get flowing through it, which if we then put some sort of output device on using our transistor, depends on the current that we have on the base. Current flowing through it depends on the current that we have on the base. Okay, so let's look at our transistor in a form of a question. So I've got a transistor circuit here with a lamp and I've got a light sensor. No, I have not missed it out. I have not connected them to start with. Okay. So first of all, if we say if the transistor is just saturated, so it's just turned fully on, then what is the collector current? So if the first assumption we're going to make, well, okay, if it's just turned on, then all of that our voltage must be across the lamp. So in that case, we must have 900 milliamps flowing down through it. Okay, we assume if this is fully turned on, just fully turned on, there must be 900 milliamps down flowing through it. Okay, so let's work out what the current in the base is going to be. Or to work out IB, then we use the formula IC is equal to HFE times by IB. So we can just rearrange that. So we get that. 900 milliamps divided by 500 gives me 1.8 milliamps. So we can see current control device, 1.8 milliamps just here, gives me 900 milliamps just there. So what we're aiming to find now is what is going to be the V in. Okay, so in calculating V in, well, we're making the assumption that the voltage on the base is going to be approximately 0.7 of a volt. So the voltage just here is about 0.7 of a volt. Okay. We need that, so alongside, so the voltage across the 1 kilo ohm resistor, the voltage equals current times resistance, and in this case it's our base current, so 1.8 milliamps times by a 1k resistor, so that's 1.8 volts. So therefore, using the assumed voltage just here, then we can say, well, V in is just going to be the combination of the two. So V in equals 0.7 plus our 1.8 volts. Gives us 2.5 volts. Happy days. So now let's look at this part of the circuit. So if we look at our light sensor, given that value there of 1k, and in dark we can say our LDR has a resistance of 3k. So what I want to know is what's the voltage when it's dark in the middle of our potential divider, so that when we connect it to here, we know whether we've designed our light sensor correctly or not. Oh. So using our just our ratio method, you can use the long-handed if you like, but R2 would be our LDR. So I work out that we've got 6.75 volts coming from our light sensor. Okay, why have I done that? Well, okay, so we're going to connect both parts of the system together. So I'm going to connect this to here. So here we said that we need 2.5 volts here for the lamp to be on, and this gives us 6.75 volts when it starts. So it seems okay, but I want to do a little bit further analysis to prove that when we connect the two subsystems together, we're not going to experience any problems. How do we do that? So for us to understand this, we're going to use Thevenins. Yay! So we're going to do our Thevenin circuit. So I've just done a very quick sketch of it. So our voltage open circuit, if you remember from Thevenin's, is just what voltage here we would expect to get over on our load. So we've already worked that out to be 6.75 volts. Then we're going to calculate current short circuit. That's as though we're then shorting out our load. So we've got all of our voltage across that one. Then I've calculated the current. So we've got 9 milliamps. So then our equivalent resistance is voltage open circuit divided by current short circuit, which is 700. Oh, really write it out, shouldn't I? 6.75 over 9 milliamps equals 750 ohms. I'm just going to do a quick check and see what 1k in parallel with 3k gives me. So I got the same answer. So I can now look at start to draw my Thevenin's equivalent circuit. So I've drawn my Thevenin's equivalent circuit there. So 6.75, 750 ohms, and then my load is my transistor. My load is my transistor circuit. So it's my transistor input resistance. Now don't get fooled. That's going to be V in divided by IB. Okay, so resistance is equal to V divided by I. So we've got V in divided by IB. Okay, what was that? I can't remember. 2.5 volts was our V in that we worked out to be, and our IB was 1.8 milliamps. So that gives me 1389 ohms, rounding up. Okay. So we're just going to calculate the voltage across the load. Now we know these two resistances, so we can use our quick ratio method. So voltage across our load then is going to be R2, so that's going to be what, 389 divided by our 750 plus 1389 times by the voltage that we got, 6.75 volts. Okay, gives us an answer of 4.38 volts. Okay. What do you think? Is this circuit going to work okay? Well, originally we said that we needed our 2.5 volts there. So now we've connected the two circuits together. We haven't got quite the voltage that we expected, the 6.75, but what we have got is still greater than the 2.5 volts. So the lamp should work fine. Okay, that'll do us for our transistors.